Why are some kids sad? What makes the wind blow? How do birds fly? Our world is full of curious phenomena. To find answers or solve problems, we can use a process which was first acknowledged by the scientist and philosopher Ibn al-Haytham in the 11th century. Also known as Alhazen, he is considered to be the father of optics and the scientific method. There are 6 steps to it. 1. Observe and ask questions. 2. Research. 3. Formulate a hypothesis. 4. Test your hypothesis. 5. Conclude. 6. Share results. The goal of the scientific method is to find out the truth. Let's try. Step 1. Observe and question. Observation helps us formulate challenging questions that you will be able to test. A good question converts the natural sense of wonder into a focused line of investigation. When is the best time to drive to school? Which food is my dog's favorite? For example, if you observe that women smile more often than men, you might ask, why do women smile more often? Step 2. Research. Find out if other people have asked the same or similar questions. If you research online, use search terms like study, research, or meta-analysis, which is a summary of research for a specific topic. Read as much as you can about your particular subject to see what you can find out about. For example, research happiness based on gender or study the science of smiling in different cultural contexts. Step 3. Formulate a hypothesis. A hypothesis is a theory that you can test to see if your prediction is right or wrong. From your observation, you have noticed that women smile more often and that people who are smiling seem to be happy. From your research, you know that there are different types of smiles: shy, genuine, and false. In one paper, you read that baby girls smile more often than baby boys. Here is a hypothesis. Women smile more than men because they are happier than men. Step 4. Test your hypothesis. When you test your hypothesis, you want to make sure to do this in a fair way and that the conditions are constant. For this hypothesis, we can design a test where an interviewer talks with a set of men and women for 5 minutes each, counts how many times they smile, and then asks each one to rate their level of happiness. To get a good sample of the population, we invite 300 women and 300 men. Seems like a good test, right? But wait, what if the interviewer is a woman and men tend to smile more at women? Or vice versa? Or what if the topic discussed is one that interests women more than men? And what if people aren't reliable reporters of their actual level of happiness? So clearly, we would need to be much more careful. Step 5. Analyze and conclude. Let's assume that you designed a very careful experiment, controlling for as many variables as possible. Now you can analyze the data to see if your hypothesis is correct or incorrect. Depending on your findings, you may want to change your hypothesis or change the design of your testing. Perhaps you have discovered an even more interesting question. This stage of the scientific method can be repeated as many times as necessary until you find just the right hypothesis and test method to find accurate results. Step 6. Share the results. When you are satisfied that you have proven or disproven something important, report your results. In science, it is important to detail your methods so that your peers can review your work, which is a critical step to getting published. If your results are solid, your experiment can be repeated by other scientists. Such reproducibility is a sign of good scientific work. But failed results can also be interesting. An incorrect prediction could prove to be important and should always be reported. To make sure you get it completely right, here are 3 more things you can check before you publish. A. Any scientific theory is falsifiable. Real scientists know that there is no such thing as a scientific proof. In other words, you can never prove your theory to be 100% right. All you can do is find a lot of supporting evidence that it could be correct. Here is one example. Say that someone says, hamsters can fly. We cannot prove that this is false. Yes, we have never seen a hamster fly, but we can't test all possible conditions or look in all possible places on the planet to know that all hamsters never fly. Maybe a space hamster does. So while we can often prove that a phenomenon exists, it's much harder to prove the non-existence of something. If your theory can't possibly be proven wrong, then it's not falsifiable and hence not scientific. B. Correlation is not causation. When you analyze your results, it is important to separate between two possible reasons: correlation or causation. Let's say you hear that towns that have more churches also have more bars. Could it be that religion makes people want to drink, or that drinking helps people to find God? If you add more facts, such as larger towns have both more bars and more churches, you can see that a larger population is a more likely cause of higher numbers of bars and churches. There is probably a correlation, but no causation. If we compare men with women and would conclude that women smile more and are more happy, then this still doesn't mean that it's happiness that makes them smile. Maybe they just eat more chocolate and cookies, which makes them both happy and smile a lot. C. Avoid selective windowing. When you publish, you've got to show all relevant facts. Colgate once ran an advertising campaign claiming that 80% of dentists recommend Colgate. What they didn't tell us is that when they asked dentists to select their preferred toothpaste, Colgate was just one of many other brands they also recommended. Colgate was later sued and forced to take down their misleading ads. The purpose of science is always to find out the truth and nothing but the truth. To use science to mislead us is wrong and terrible business practice. Let's do a last example together. I have 2 coins. One is bigger. Why? The small coin says 1 cent, the bigger one says 5. Aha! Small coins are worth less money. Bigger coins are worth more money. I pull some more coins from my pocket. 2 more pennies, 1 more nickel, and a $quarter, which is 25 cents. Great, my hypothesis seems true. But wait, is the quarter worth more because it is bigger? So is that a correlation or a causation? My sample size is pretty small. I don't think I am ready to report my results. Can you help out? Please apply the scientific method to study your local currency. Maybe you have a hypothesis that we can test until we get solid, repeatable results to report.